So for chapter 5, important key that we will touch on will be lift and drag concept. What is friction drag? What is pressure drag? How to get drag coefficient? What is the pressure distribution and introduction of boundary layer? I think introduction to boundary layer already covered in 3179. Okay, so important you understand what's lift and drag. Okay, these two video is more on the wind tunnel testing to see how the flow inside the wind tunnel. Now, chapter 5, the title for chapter 5 is flow over immersed body. So immersed body means you're inside a liquid. It's not necessarily inside air. It can be inside water. It can inside oil. It can inside petrol. Anything that have density, then you can fall within this chapter. Okay, this chapter 5 is flow over immersed body. So experiment, this video you can watch it later in my PowerPoint slides. Before we study about the lift and drag, there are 3 categories of analysis. As you can see, you start exposing to ANSYS software. The first diagram on the left-hand side is a 2D scenario. 2D scenario or two-dimensional scenario that you only consider what is happening to y and x or other two axes. It can be y and x, it can be z and y, it can be z and x. But normally, as a standard case, we will use x and y axis to represent a 2D dimension cases. Okay, if you have a 2D scenario, then you're having a diagram on the left-hand side A. If the flow inside an asymmetric scenario, as you can see here, asymmetric means if you see the U, the flow go in touch of a bullet shape kind of body. Asymmetric means that no matter how you cut the body, you will still see the same profile. For example, maybe my drawing is not very good. You cut this body into half. You are still seeing top and bottom still the same. Okay. If you cut the body into half, the shape that you get still the same. The airflow from the front go up and go down will be the same with the bottom diagram. The flow will flow like the same. You're seeing the similar behavior if you're having an asymmetric scenario, meaning you cut on the plane itself. For example, you cut on the Z and X plane into half. This is XZ plane. You can divide the body into the red color object, one on the top, one at the bottom. However, because this is an asymmetric scenario, meaning the result you get from the analysis will be the same for the top and bottom. Another scenario, you can cut this object by using Y and X plane, where you cut asymmetric body using a plane. Let's say you cut the plane in XY plane. So this is XY plane. So when you cut XY plane for asymmetric, you'll get left and right body. Okay, so I'm not going to draw, but it will be the same scenario as the top and bottom, but this time it's on the left and right. Okay, the third scenario for the flow, you have a three-dimensional or 3D, meaning the air come from the front and it hit all the different component of that particular subject. For example, this aircraft. So the shape is different at different location, meaning no matter how you cut using XY plane, ZX plane, or 2D plane, you cut, no matter how you cut, you do not get the same shape as a top, bottom, left, and right. So three-dimensional is a very complex scenario. Okay, now this is in your second assignment where you are analyzing a three-dimensional cases. Okay, your first assignment will be a two-dimensional, or you can say as a asymmetric scenario. Okay, your first assignment is 2D case. Your second assignment is a 3D case. All right. So I think from the diagram itself, you're able to differentiate what is 2D, what is asymmetric, and 3D. Okay, let's look at very important concept about lift and drag. Okay, now how you define lift and drag? Lift and drag itself is a force. It's a force in terms of direction of the upstream velocity. Force and the velocity. Okay, now one is in the direction, it means parallel to the velocity. Another one is normal. Normal, what mean by normal? It means if the velocity in this direction, normal means 90 degree. So this arrow represent lift. This arrow, if it's along the V direction, it represent drag. Okay, so just test yourself by using these two definition. What is lift? What is drag? Because it's important. Because in coming test or exam, you're going to need to define what is lift and drag. Okay. All right. Now let's say I give you a flow in this direction. Let's say your Q or your V means your airflow flow in this direction. And you're having an object with this. Let's say you're having an object here. Okay. Maybe I draw it like this, a square. Let's say I'm having a 2D scenario. I have my Y and X. This is my Y, this is your X. Let's say we have 2D scenario. Your flow is flowing, okay, your flow is flowing from the left, from the right to left with a V. Now my question is that, let's say you are, because of this flow, you are generating two type of force on this red color object. Okay, so if you see this one, if you look at the definition, which one is your lift, which one is your drag? Okay, ask yourself. First one, it is 90 degree to the flow. What is this? I label as A. Another one is this, maybe this way. Okay, this is your B. Okay, cool. What is A force? Is A force a drag or is A force a lift according to this scenario? Is a lift or it is a drag force? Which one? Who are you there? I'm referring to A. This one. This. So A is what? A is lift or drag?
Leaf.
Leaf, because it is 90 degree to the velocity. Okay, then what about B? B is what, Ku?
Draft.
Drag, so
Drag.
B is drag, because definition for drag is in the direction of velocity. It means velocity go to the left, it will go along. Okay, normally the drag will go against lah. Okay, it will go against, but just to get the concept right, important is parallel to the velocity. But most of the time it will fight against the velocity. Okay, most of the time this is drag, this is lift. Now, once you understand this concept, I think you have done for chapter 5. Okay, because the rest is just mathematics derivation for what is lift, what is drag, and then you will come across the differentiation and integration. Okay, what I asked Ku just now is a very important question. As long as you can understand what is lift, what is drag, then you are right. Okay, so if you draw a diagram like that, if you're given an airfoil, you should know what is your lift, what is your drag. Okay, now from your assignment 1, you should know where is drag, what is lift already. Okay, from today lecture, you should able to understand what is lift, what is drag. Okay. Another thing is consider in this chapter will be a shear stress, a body shear stress or wall shear stress. We give a symbol of shear with a W, means wall or surface shear stress. Okay, the word shear, again, recall the concept of shear stress and normal stress. Let's say you have two body, and this is your area. Same, this is also area. Let's say you have two forces. The first scenario, if the force is 90 degree to the area, this case we call it normal stress. Okay, with this F and area 90 degree, the product of normal stress will be force divided by area. Okay, force divided by area. Another one, we call it shear stress. I'm going to change color. What mean by shear stress, or the word shear? I'm going to use blue color. Let's say you have the same magnitude of force. However, now the force is parallel to the area. Then the product of this case, we call it shear stress. How you calculate shear stress or shear stress equal, same formula, you take force divided by area. Okay, what is different between normal stress and shear stress is the direction of the force. Okay, now if you compare the definition I explained just now between normal stress and shear stress, then if the movement of the force is along the body or parallel to the surface, it will always fall under shear stress, or we call it wall shear stress. Okay, now another side note is that how we define the forces, or this one, okay, this force here, how we call this force that define the normal stress. This force we call it normal force. Because it's 90 degree to the area. What do we call this blue color force that give you shear stress? We call it shear force. Both is force. Apologize for my writing. shear force. Both also F, but by looking at the text itself, normal means 90 degree. Shear force means the force is parallel to the area. Okay, so this is an important concept that you need to always remind yourself. When you can name it as shear force, when you can name it as shear stress, and so on. Okay. All right. Now, if you study about lift and drag, normally you will come across a pressure distribution. Okay, a pressure distribution. So an example that you see on the lower corner of your screen, you see the U will always we call it upstream velocity. Upstream means the one that enter into the system, upstream. This is downstream. At the back, we call it downstream. The word is come from a flow, a water flow. So if you go up the hill, so this is uphill, the water will flow from the hill, high ground to the low ground. So this is called upstream. This is called downstream. Okay, so the pressure distribution, as you can see here, there's a different pressure on the top and bottom. And what happened to the shear stress, if you want to draw the wall shear stress, is what you see on the screen here. Okay, the arrow will go along the surfaces. Okay. Now the next one is all more on the derivation on the equation for the lift and drag. So I will go through for the lift. You apply the same for the drag. Okay, I'll go slow on the lift first, then I'll go very fast for the drag concept. As you can see on the diagram on the bottom of your screen here. Okay, let's say we take a very small portion on the airfoil and we enlarge it into this diagram. Okay, so this gray color with the blue line here, it means it's a surface. And then we only focus on very, very small area. So here to here is dx. Dx means very, very small displacement, or this small distance. And what is important for us is focus on the area. Okay. Now, before that, just now we mentioned about pressure. We know that if we have a flow along the surface, there's a change of pressure. What is the definition of pressure? You take force divided by area. However, we are more interested when we derive. Every time we derive formula, either in physics or in other engineering module, we like to convert into forces. Okay, we need to put our equation in forces term. So what you do, you put your force in the term of area and pressure. So you rewrite this definition: force equal to pressure times area. So you look at this diagram. So how do you define the pressure forces? Okay, you take pressure times the area, and the arrow always pointing pressure. Definition of pressure when you study about control volume. Still remember I mentioned that pressure, how pressure act on the body. Pressure always point to the surface. So when you convert pressure into forces, still the same. The force always point to the surface. So that's why the arrow is pointing to the surface here. Okay, so we have two forces on the surface here. One is because of the pressure, P, already convert to forces. Another is due to wall shear stress. Wall shear stress also convert to force. Forces due to shear stress. Okay, now recall just now, what is shear? Shear also force divided by area. Shear is something that go parallel to the area just now. Okay, how do you convert something back to the force that we like in derivation? So you write force equal shear times area. So same, you are seeing shear times area, get force. So basically, the diagram that you see on the left-hand side, this is a free body diagram with forces. Consists of pressure and shear stress. Under effect of pressure and wall shear stress. So you need to convert, when you draw free body diagram, you're interested in forces only. Okay? All right. The next one will be, you put everything in X and Y direction. So you're seeing the X and Y direction with the angle. So what are the forces in X direction? First, you convert this one. You convert this one to X and Y direction. Okay, with an angle theta. So this is P dA. This is X direction. Okay. This is Y direction. So how do you get the resultant in X direction? So you split this one to X and Y. So X1 is cos, right? So P dA times cos theta. All right. You do the same for shear stress here. You do the same. So you're having the X direction and Y direction. In this case, your shear stress going up like that. Of course, you already converted to forces already. So you need to split this one into X and Y also. With theta. Okay. Theta. No, it should be, let me see here. Here it should be. Okay, let me draft something here. So you will have, so your theta over here, you have here. Yeah, correct. F Y is sine. Oh yeah. Okay. So this is theta. So you're having like that. Okay. By the way, we will come back to this one. This is more on mathematics. Okay. All right. So you will get stress dA sine theta, where you convert this one to X direction. So you get this expansion. Then you do for the Y. Also, you will get sine and cos relationship. Okay, then you integrate. As you can know, just now, what is lift and drag just now? Basically, you know that this is a direction of your U. This is a direction of your velocity, U. So the one that go parallel, this one will become drag, or the direction to X will become drag, or the direction to normal to the velocity will become lift. So dF will become drag. dF is the small changes of X. When you want to find the total drag, what you do? You integrate. You integrate dF. Same you do for the Y. You integrate the F component, you'll get lift. Okay. Okay. Next, we look at one example, then we call it a day, right? Give me another 5 minutes, then we stop for the day. All right. Now, you given an example. So you look at the screen here, you have a plate here. So this plate is inside a velocity. So the arrow of velocity is U and U equal to 25. Pressure at this point is 0 gauge, means 0 gauge means there is no increase of pressure. It means you install a pressure sensor here, the reading will be 0. Pressure sensor, at this point, there is no increase of pressure, 0 gauge. Then you have a plate here, and you have a pressure acting on the surface here. Okay, pressure acting on surface here. And you have a Y and X direction. You are given the shear stress equation, wall shear stress equation, given by 1.24 times 10 power negative 3 divided by square root of your X. X is in meter. All right. Now you have two scenarios. One is along the U velocity. Another one you see on the left-hand side diagram here, you have case A and case B. Case B, you have the same velocity. However, you orientate the plate to a vertical position. Then you will have a pressure equation given on this side, given by this equation. And the pressure at the back is measured by negative 893. And you're given the equation of the wall shear stress. Right. Now, the tutorial question asks us to calculate what? It asks us to determine the lift and drag on the plate. Okay, how do we determine the lift and drag based on the plate itself? Okay, now from what we covered just now, lift drag is result from two things only: pressure and wall shear stress. And also by looking at the direction compared to the velocity. If it's parallel, go along the velocity, it becomes drag. If it's become normal to the velocity, become lift. Now this concept, and then we will derive the equation. Okay, you see how we solve it. We solve for the case scenario A first. So if you look at the parallel plate, we divide into top and bottom surface. So if you look at the bottom surface, the angle that we look at is 90 degree compared to the upstream here. And then the bottom one will be 270. Okay, if you look at the pressure magnitude there. Okay, so if you look at this lecture diagram that we covered just now, so as you can see, the angle is measured from X to the pressure magnitude there. Okay, X to pressure magnitude there. All right. So what you do, if you compare to the top surface, this one, to the top, the angle will be 90 degree. Okay, the angle is measured from x-axis to the pressure magnitude. As you can see, the pressure is pointing down, so the angle here is 90 degree. At the bottom, the arrow is pointing up, so it becomes 270 degree. Okay, so if you turn the object, if you measure from here to here, you will get 270 degree. Okay, the first one is 90 degree because the pressure pointing down. You calculate the angle from x-axis up to the pressure arrow pointing down. Then bottom one, also you look at the pressure arrow. You calculate from x-axis until the pressure arrow. So at least you understand why 90 degree, why 270 degree. Then you apply the equation that we just learned just now. So your lift is integration of the force on top of the surface and bottom of the surface. Now you should know why top and bottom now, because lift is normal to the velocity. So you just put in lift equal to integrate top minus PdA, because how you get force? You take force and dA. Okay. And the bottom one is pressure. Bottom is pressure. So if you balance this equation, there's no lift generated for this object. Lift equals 0. Now what about drag? Drag, you do the same. Integration of top and bottom, the F also. However, this time we will use wall shear stress. Wall shear stress will contribute to drag. Pressure contribute to lift. Okay, pressure contribute to lift. Wall shear stress contribute to drag. Okay. Then you put in the equation there. The equation equal to this one. So if you top and bottom actually is the same because the arrow direction is the same. Okay, arrow direction is the same. So you have two integration of the wall shear stress dA. How you calculate dA to the x there? So you expand. Okay, you expand this one to 10 times dx. Why 10? Because the question give you the width is 10 meter. So that's why there is a 10 there. Okay, width times distance, you get area. Is the dA. Then this one is your shear stress equation. Okay, and then call back the integration scale. You integrate, you will get this number. Okay, you get the track. So what you learn from this tutorial? Shear stress, wall shear stress give you drag. Pressure give you lift. Okay, you repeat the same concept for another one. Now the angle is 0 degree for the top, for the front, 180 degree for the back. By looking at the actual diagram, this one, okay. So angle 0, 180 degree. You do the same. Lift equal to force front plus back. In this case, you see the lift. The lift is due to the, sorry, I apologize. You have to see the direction of the force, the stress that you have here. So as you can see, the second case, when you have a perpendicular cases, we are using wall shear stress instead of pressure. Okay, I go back to the previous example. You see, when you calculate forces for lift, because the pressure direction is perpendicular to x direction, the forces you have here is pressure and drag. But you can ask, what happened to the wall shear stress? The wall shear stress, do it contribute to lift or not? Do it contribute to lift? The answer is very low, because our definition for lift is perpendicular to any forces that perpendicular to your velocity. So if your wall shear stress is along the U, it will not become U. Yeah. So, or in other cases, if in the exam you're given this hybrid condition where you have a 45-degree from the x-axis or the U direction, then when you calculate lift and drag, you need to be careful when you need to combine pressure and wall shear stress at particular direction. So lift these two in x direction, it will become drag. If these two in y direction or perpendicular to the flow, it will become lift. Okay, yeah? So just take note on this one. So that's why in the second example that is perpendicular, in this case, we will use the shear stress, wall shear stress instead of the pressure, because lift is normal, any forces that normal to the velocity, and it becomes lift. This combination will give you lift. Okay, so in this case, that's why in the second scenario B, we use wall shear stress. Yeah, right. So just take home idea. What can contribute to lift and drag? Pressure and wall shear stress. How you know these two will generate lift or drag? You need to convert to forces, either from pressure or wall shear stress. You look at their direction. If it's perpendicular, it becomes lift. If it goes along the flow, it becomes drag. Okay, this is just a reminder. Okay, then we follow along. This one minus this one is the same, get 0. Then for the drag, you can see this one, this time we use pressure because the pressure when you convert to force is go along the U. So that's why in this case, the drag will become only contribute by the pressure. So this one minus this one. And this case, you have the front and back. Front pressure, you substitute in the front. At the back pressure, you substitute here. Again, how do you get 10 times dx? These two will give you dA because the width is 10. Then after that, you'll get the value of drag. Okay, so I think we will stop here.